The citizens of our nation face uncertain times. Power-hungry leaders, both to the east and to the west, cast long shadows, making existence difficult for many. It is therefore the duty of every household to be prepared and keep at hand a reserve of drinking water and food, ensuring that the essentials of life are within reach in case of an emergency. A supply should include a battery-powered wireless receiver and, of course, a Radiacode device. Not only can this item be used to determine the safety of food and surroundings, it can also provide entertainment during the long nuclear winter evenings through parlor pastimes such as Guess the Dose and the Compton effect. Should the warning sirens sound, citizens are instructed to find shelter and await further instructions.
Hey everyone! Today I'm going to do things a bit differently. Instead of discussing the wave behavior of light, I'm going to take a look at how electromagnetic radiation can also be very particle-like. And for this, we're going all the way to the far end of the electromagnetic spectrum and use a small but powerful X and gamma ray detector, the Radiacode 110. Now, before you think this is a sponsored video, rest assured it's not. So any enthusiasm on my side about this device is purely because of my own personal experiences. Now, in the first half of this video we're going to goof around a bit, but in the second half I'm going to do a few serious experiments, such as coincidence measurements and Compton scattering. Radiacode devices are available in different types, but they are all intended to detect X and gamma rays, so very high frequency electromagnetic radiation. I think it's good to emphasize that these devices cannot detect other common types of radioactivity, such as alpha and beta radiation, because the working principle is just not suitable to detect these. The underlying principle is actually not that complicated. Inside the device is a so-called scintillation crystal that can absorb the high-frequency radiation. The absorption of a quantum of radiative energy results in an ionization track inside the scintillator, which creates many excited state molecules. And when these excited states fall down to the ground state, they emit visible light. And this light can be detected with a very sensitive photodetector attached to the crystal as a little flash. Now, if you look at the energies involved, X and gamma ray photons can contain tens of thousands to even several millions of electron volts, whereas a photon of visible light corresponds to only around 2 electron volts of energy on average. So a single high energy photon can in principle cause the emission of a lot of visible photons. The total visible light in a detection event can now be integrated, and the resulting value is a measure for the energy that was originally in the high energy photon. And if we collect the values for all the detections and sort them into small bins based on their energy content, it allows for the creation of a detailed spectrum of the high energy radiation that is absorbed. The Radiacode can in this way identify X and gamma rays in the range of say 3 to 2800 kilo electron volt, and this allows for the identification of the elements that cause the radiation by looking at the emission peaks in the spectrum. On top of that, it has a built-in GPS and comes with excellent software. Now, since the weather outside is very inviting, let's do a little experiment to demonstrate the high sensitivity and the GPS functionality. So I'm here at the Princess Alexia tunnel, named after a cute Dutch princess, and it's here that we're going to do an experiment. I want to show you that the radioactivity level inside the tunnel is actually higher than at ground level. We're going to use the map function of the Radiacode for this experiment. So while walking through the tunnel, the device records radiation levels every few seconds. And here you see the result of our test presented on a map showing the radioactivity as a function of position while going back and forth through the tunnel. The GPS struggles a bit to determine the position inside the tunnel, but that of course is to be expected due to the poor reception underground. Now it's clear that the highest radiation levels are inside the tunnel, and that is because a significant part of the background radiation originates from minerals. And of course, inside a tunnel there are in fact more mineral materials surrounding you than outside. Also, this tunnel contains a lot of concrete, which can contain radioactive radon gas. The radiation level in the tunnel is comparable to the radiation levels inside my house, so there's no reason for alarm. But I think this feature can be extremely useful when you want to be aware of the radiation levels in specific areas. Now, I promised that we're going to do several experiments, and for these we first need to acquire a radioactive source. I noticed that my neighbor Ramon had some uranium glassware on his windowsill, and he was so kind to donate this glass to me. Now, uranium glass fluoresces brightly green under UV radiation, which I guess is what makes it attractive. But it turns out to be only very mildly radioactive. I need to insert the radiacode into the glass to really detect somewhat increased radioactivity. However, if we collect spectral data for a few hours, we can in fact recognize the spectral characteristics of the uranium decay chain. But unfortunately, this glass is not radioactive enough to do any of the upcoming experiments. So let's head out to the thrift shop and see if we can find something a bit more spicy. Unfortunately, no highly radioactive glassware or pottery here, but I did find this gas lantern. Inside the lantern is a little mantle that contains thorium oxide, which is mildly radioactive. The mantle in the lamp turned out to be broken, but for our purposes that's not really a problem. Now, if we collect the spectrum of the mantle, it is indeed indicative of thorium-232. As with the uranium glass, the radiation levels are quite low, so you need to collect these data over several hours. So this material is also too weak to serve as a radiation source for our experiments. But luckily I also found these two ancient smoke detector units in the thrift shop. The radioactivity of these can easily be detected even from outside the packaging. They were manufactured in 1989 and have apparently never been used since the original battery was still inside them, but despite their age they still work just fine. Holy moly! Now, contrary to modern smoke detectors that are all based on an optical principle, these old smoke detectors use ionization with alpha radiation to detect the presence of smoke particles. The little ionization chamber contains a tiny amount of Americium-241, around 300 nanograms, which decays mainly by the emission of alpha particles to Neptunium-237. The half-life of the Americium is 433 years, so we won't have to worry that the radiation will run out anytime soon. In fact, I calculated that even after 37 years, 300 nanograms still emits approximately 35,000 alpha particles every second. But apart from alpha radiation, which of course we cannot detect with the Radiacode, it also emits some pretty significant X-rays. And if you look at the X-ray emission spectrum of Americium-241, the most prominent emission lines are found at the lower end of the spectral range of the Radiacode, at around 26.4 and 59.5 kilo electron volt. Now, I must admit that I have very little knowledge of radioactivity, and I found it fascinating that it's completely hidden from our senses. The human body is just not equipped to pick up on it until it's basically too late. However, as a phenomenon, it's present everywhere. But I guess the biggest surprise for me personally is how differently it behaves compared to lower frequency radiation like visible light or radio waves. So let me try to illustrate this quickly. Say that we have an emitter of radio waves. The emitter works by accelerating charge in, for example, an antenna, which results in the emission of electromagnetic waves in basically all directions. The field appears to be continuous, and it will not surprise anyone that multiple receivers can detect exactly the same field variations simultaneously. Of course, the further a receiver is away from the transmitter, the lower the intensity of the radiation of the signal, but signals remain, as far as we can measure, continuous, even if signals are received from a transmitter that is 25 billion kilometers away. What we notice is that the field intensity falls off with 1 over the square of the distance from the transmitter, and this can be understood purely from geometry. It's because the receiver picks up on the radiative power over a small part of the total area of a sphere. If we now move to the visible light region, where the frequencies involved are approximately 8 orders of magnitude higher than in the average radio wave, we observe clear quantization in the interaction between field and matter. This results, for example, in distinct emission and absorption lines in atomic spectra. However, when you consider propagation of visible light through space, it still behaves very much like a wave. Here you see, for example, how coherent laser light makes its way through the hundreds of tiny pinholes in a photon sieve to predominantly end up in one point due to wave interference. So from this perspective, it is very tempting to state that quantization is a property of the interaction and not intrinsic to the electromagnetic field. However, if we increase the emission frequencies another 4 orders of magnitude, this view seems to completely fall apart, because the behavior of X-rays couldn't be more different than that of radio waves. Here, radiation is clearly both emitted and received in the form of discrete packages that involve a substantial amount of energy. And if you consider the emission of X-ray radiation from a classical perspective, it seems impossible that the energy involved in the absorption can just pop out of the field at the emitter. So here, a particle approach actually makes much more sense. Yet even with X-rays, we still observe typical wave phenomena like, for example, diffraction. What I want to do next is do a few experiments from which you can hopefully draw your own conclusions about the following question. Is the quantization found in the interaction between electromagnetic field and matter intrinsic to the interaction, or is it a fundamental property of the field? Before we can do meaningful experiments, we need to lower the background radiation level observed by our detectors a bit. It's because it's relatively high compared to the intensity of the radiation source we will use for the experiments, which is in this case the Americium from the smoke detector. So to do this, I decided to make LED radiation shields for the Radiacode to minimize the effect of the background. One thing I feel I need to mention is that if you work with lead, always wear gloves and collect all the lead chips and oxide, and either recycle it or bring it in as chemical waste. You don't want lead to end up in the environment because of its cumulative toxicity in plants, animals and humans. Adding lead shielding really helps in bringing down the background radiation count. Here you see what happens to the count rate when I insert the device into a lead shield. The detection count drops from average values to above 10 counts per second down to say 1 count per second, which you can see here in this graph. At the same time, the hardness of the radioactivity increases, which is due to the fact that only the more energetic X and gamma rays make it through the lead. Okay, the first experiment we'll do is check whether the inverse square law we just discussed for radio waves still applies for X-rays. And the way we'll do this is shown schematically in this image. We'll measure the counts per second as a function of the distance r between the detector and the Americium source. Note that the detector is inside a lead enclosure with a fixed aperture of 8 mm through which the X-rays can pass. We should be able to fit the measurements to an inverse square law as shown here. The constant A is basically a scaling factor that accounts for the sensitivity of the detector and the intensity of the source. B is the background level that we need as an offset. In the current configuration it has a value of around 1 count per second. And this C is a correction for the position where the radiation will generally be absorbed in the scintillation crystal with respect to the center of the device. Basically, it would indicate where, on average, most of the radiation of the Americium is absorbed in the scintillation crystal. So now we can do the measurements by moving the source in steps towards the detector and measure the average count rates. Here are the results of the measurements, and we can now fit these quite well using the following values for A, B and C. And as you can see, I found 4 mm for C, which would mean that most of the radiation is absorbed in the site closest to the source. But from this measurement, we can conclude that the inverse square law also applies to X-rays. Okay, our next experiment is about the correlation between detection events, and to demonstrate this, I actually need two Radiacode devices. I just showed you the example for radio waves where every receiver detects the same or at least a strongly related signal. But if you look at X-ray detections in general, the clicks seem relatively random, both for a single detector as well as between different detectors. But are these signals truly random and unrelated? For example, if you think in terms of waves that can set off detectors with a certain probability, two detections might be slightly related to each other at some fundamental level. However, it would not be very obvious when the probability of detection is very low in general. So what do you think? Are the detections of the emissions by a single X-ray source measured by two different detectors completely unrelated? Well, let's find out. Let me state that this is by far the hardest experiment demonstrated in this video, because you have to measure what is called the second order correlation function between detections made by two different detectors. I've actually explained in detail how this type of measurement works in a previous video, but in short, we can record the time that each pulse arrives at detector 1 and make this our reference value. We can then examine the distribution of pulses from detector 2 within a specific time range or interval delta t and establish the time difference tau for every pulse by detector 2. And we can repeat this process for every pulse made by detector 1. And in the case that the events between the two detectors are truly random, we will statistically find a uniform distribution over all time differences. However, if pulses between detectors are somehow related to each other, there will be an increased value for the probability around a specific time difference, which in the case that detectors are at equal distances from an emitter would be around 0. To do this experiment, we have to take a few hurdles. As far as I know, the Radiacode does not allow accurate time logging of individual pulses by default. Also, I could not find any existing software that could extract these data from the device. Now, the easiest way would be just to record the audio clicks of the devices or record the flashes of the LEDs using a scope or a sound card. But it turns out that both the clicks as well as the flashes are not very well defined events. The clicks are actually an audio sample that is played back with each detection, and the flash of the LED is some kind of rectified version of the audio sample. So these are not very suitable to extract accurate timing of detection events. However, if we open up the device, we can identify this test pad here that contains a very short digital pulse of 3.3 volts and around 5 to 7 microseconds long for each detection made by the device. And this signal does not contain any information about the photon energy, but for the type of coincidence measurements that we're trying to do, that is not really essential. So what I did was solder a wire to the pad in question and another wire to the ground plane of the device. I then wired both these to a connector that I glued in the housing with a 220 ohm resistor to limit the current in case of an external short. And now we have a Radiacode with a connector that allows us to collect detection data with a very high temporal resolution. We can now feed the signals into an Arduino and then time them using the internal counter that is synced to the clock frequency of the processor. Here you cannot just use the loop function of the Arduino because it's way too slow to catch 5 microsecond pulses. So instead I configured two inputs that have interrupt capability, and this then allows for the detection of signals with very high precision. If you correct for code execution times, you can actually time pulses within 24 nanoseconds precision. By trial and error, I found the Arduino Duo to work much better than an Arduino Uno or a Mega. The Uno has very limited memory, the Mega constantly gave issues with timing accuracy, but the Duo worked like a charm. Also, it has a clock frequency that is much higher, so it can time the pulses with greater accuracy. So what I made the Arduino do is create a timestamp for each individual detection by either detector and then export those data as two lists of clock cycles using the serial monitor in the Arduino IDE. And we can then use these data sets to evaluate correlation between pulses. I will place a link in the description to all the code that I used for this. I did several measurements in the configuration that is shown here. This is the Americium source. Below it are two detectors in a LED enclosure with an aperture of 8 mm diameter directed towards the source. In the background, the Arduino Duo connected to a PC. So let's now take a look at the data that was collected. Okay, so in this measurement, detections between two detectors seem unrelated to each other. You might say, isn't this here significant? But given the variations, I don't think so. Here's another graph from a different set of data and presented on another timescale, but this set also does not show any clear relationship between detections by two detectors. Now in hindsight, this result might seem trivial to some of you, but let me assure you that it's not. I only got this result because I chose the intensity of the source to be much higher than that of the background radiation, about a factor of 20. And this is something I discovered by accident, and I really want to show you because it's quite surprising. So before actually checking for any correlation in the background radiation, I basically expected this also to be completely random as well. However, it turned out that the signals from background radiation are actually quite strongly correlated. Here you see the correlation effect displayed on two different timescales. It's not like some marginal effect, it's like boom, right in your face. Now, in search of an explanation, I found that this is in fact a well-known phenomenon because a part of the background signal originates from cosmic high-energy rays or particles, and upon entry in the atmosphere, these can cause a cascade or shower of secondary high-energy radiation, which can make multiple detectors go off almost simultaneously. So the underlying reason for this type of correlation is not some wave phenomenon, but can be traced back to individual cosmic events that create a lot of secondary high-energy radiation. Anyway, finding this result is reassuring in the sense that it actually shows the setup was working correctly. The last experiment I want to do is a demonstration of Compton scattering. And this phenomenon that was discovered by Compton is actually key to understanding how X-rays interact with electrons. Compton found that if we irradiate materials like for example graphite with X-rays, we can observe two different types of scattered radiation. One part remains at the initial wavelength, whereas another part is scattered at longer wavelengths. And the wavelength of the latter radiation turned out to be related to the scattering angle. In order to arrive at the relationship that describes scattering angle and wavelength shift accurately, Compton assumed that the effect was the result of interaction of the incoming X-rays with loosely bound electrons in the material. And the only way that he could explain his observations was by assuming that the interaction is in fact an elastic collision between an electron and a light quantum, resulting in the transfer of a discrete amount of energy and momentum. So by making this assumption, Compton was able to derive a formula that describes the wavelength shift as a function of angle very well. As you can see, it contains Planck's constant, the mass of the electron and the speed of light. I don't want to go into the details of the derivation. Instead, let's look at the meaning of the formula. This delta lambda represents a wavelength shift in meters. The 1 minus cosine theta is dimensionless, so this factor here also represents a wavelength. Based on the values of these constants, we can calculate that the value of the wavelength should be 2.4 picometers, and Compton could prove that this value fitted the experimental data, and therefore we now call this the Compton wavelength of the electron. From the proposed mechanism, you can also calculate the kinetic energy and the momentum that the electron gains in the interaction with the photon, but we will leave this part out of the discussion because it was not part of the initial experiment. So to illustrate the effect, let's take a look at how billiard balls collide. I asked my father, who is a true master of the green felt, to give us a little demo with 2 billiard balls and 3 different outcomes. The white balls here represent electrons that are loosely bound to an atom, and the incoming red ball represents a high-energy X-ray photon. Now pay attention to the kinetic energy of the white electron ball after the collision and the scattering angle of the red photon ball. What you observe is that the white electron ball gains more kinetic energy with the larger scattering angle of the photon, and this in turn means that the photon ball loses more of its energy at higher scattering angles. In fact, in this demo our expert cheated a bit to keep the photon ball rolling. Now of course the comparison between billiard balls, photons and electrons is flawed in many ways, but I think it illustrates nicely how such an elastic collision works in practice. As I just mentioned, Compton did initially not measure the kinetic energy of the electrons, but only the wavelength of the X-rays as a function of angle. And here is a schematic of his setup. A LED enclosure contains an X-ray tube with a molybdenum anode that emits a sharp X-ray emission line at 17.5 kilo electron volt onto a graphite target. And the graphite will now emit scattered X-rays in all directions. But of course Compton wanted to measure the emission under a specific angle, so this meant that there would be an opening in the box. And to measure the wavelength of the scattering at different angles, the X-ray source could be rotated around the graphite target. Behind an opening in a radiation shield on this side, an X-ray spectrometer is placed that consists of a piece of calcite and an ionization chamber. And this can be used to determine the spectrum of the scattered radiation using X-ray diffraction in the calcite crystal. This is a photo of the original setup he used, showing the position of the calcite and the ionization chamber that serves as a Geiger counter. Unfortunately, we cannot see the X-ray source and graphite target since that part is shielded by the LED enclosure. And this is the result that Compton presented in one of his first papers. A slight shift in the wavelength of the radiation scattered under 90 degrees with respect to the original wavelength. In fact, he did not get this right the first time because he was confused by these other peaks. But luckily he quickly realized his mistakes and then set things straight in a follow-up article. Eventually he received the Nobel Prize for Physics in 1927 for the work he did on this subject. To do this experiment ourselves, we need to replace the spectrometer part with a radiacode and the X-ray tube with the Americium source. Now, since we're dealing with fairly low intensity radiation, we need to keep the distances short given the inverse square law. So the actual configuration looks like this. A small block of graphite about 10 mm thick is placed directly in front of a hole in the LED shielding of the detector housing. And we can now irradiate this block from different angles. I made the Americium source a bit more directional by adding a small lead pipe that creates an aperture. What we'll try to do is measure the spectrum of the scattered X-rays under different irradiation angles. In this case we'll use 0, 45, 65, 90 and 130 degrees. And here are a few images of the actual setup. Here you see the graphite taped in front of the opening in the shielding, and here I added the source. These are top views of the setup for two different scattering angles. All in all, this is a pretty basic setup really. Because the scattered radiation is quite weak, spectral data have been collected over several hours, preferably even overnight. And on top of that, we need to establish a baseline for the background radiation spectrum and subtract it from our measurements. Anyway, let's have a look at the results. This is the original emission line at 59.5 kilo electron volt. And this is the spectrum with the graphite irradiated at 0 degrees scattering angle. We observe that these are pretty much in the same location. The intensity of the peak with the graphite is just a bit lower, I guess due to the scattering of some of the radiation. We'll now rotate our beam to a 45 degrees angle. And since the detector is shielded from the direct beam, all the radiation is in principle scattered radiation. Now, because the intensity of scattered radiation is so much lower than direct irradiation by the source, I had to rescale this plot quite a bit. But compared to the spectrum at 0 degrees, the peak is indeed shifted slightly towards a lower photon energy. And this direction is in accordance with what we would expect. And here are the measurements done under 65, 90 and 130 degrees angle. The effect is pretty obvious. We observe a shift in the photon energy to lower values as the scattering angle increases. For convenience, we'll now convert photon energy to wavelength, which gives us a similar set of graphs. It's just that the shift is now in the other direction, so towards longer wavelengths. Given that on this scale the indicated dimension corresponds to 5 picometers, we can measure shifts in wavelength at the top of each peak and then plot the values of delta lambda as a function of 1 minus cosine theta, and the derivative in this plot should in principle be the Compton wavelength. So when I fitted the data, I found a value of 2.2 picometers, which is about 10% off from the theoretical value of 2.43 picometers. It's not a perfect match, but I'm more than satisfied given the hobby-bobby nature of the setup. Also, I didn't really calibrate the radiocode for these measurements. So there you have it, a demonstration of Compton scattering using nothing more than an Americium source from an old smoke detector, a small block of graphite, a radiacode and a lead shield with an aperture. Compton scattering is actually very compelling evidence for the quantization in the electromagnetic field itself. This does not automatically mean that photons are energy packets that move through space like little billiard balls, but to me it indicates that the field must retain some degree of locality and directionality in order for it to transfer energy and momentum in a quantized event. Now at this point there might be many questions on your mind. For example, why don't we observe quantization in radio waves? And the answer is that quantization can only be observed when photon energies are well above the thermal energy of matter. The thermal energy of matter is a statistical phenomenon that originates from various types of noise in, for example, detection equipment and antennas. Its value is described by the Boltzmann constant and is dependent on the temperature. When the photon energy is the same or much lower than the thermal energy, it literally becomes impossible to distinguish between individual energy states. And since the value of kT is 26 milli-electron-volts at room temperature, any quantization below this value cannot be measured, at least not at this temperature. My personal conclusion from all of this is that the electromagnetic field must indeed be fundamentally quantized, and in a way, doing these experiments myself took away a lot of my presumptions, opinions and beliefs about light. But then science should never be about beliefs or opinions. It should be about what the experiments tell us.